In this video, we work through one single continuous problem that touches every major topic in further mathematics, moving step by step from complex numbers all the way through to group theory. We start with complex numbers. We solve z squared plus 2, z plus 5 equals 0 using the quadratic formula z equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, with a equals 1, b equals 2, and c equals 5. This gives b squared minus 4ac equal to negative 16, so z equals negative 1 plus 2i, or negative 1 minus 2i. Checking, substituting either root back into the equation gives 0, confirming the solution. Next we write 3 sine x plus 4 cosine x in harmonic form as r sine of x plus alpha, where r equals the square root of 3 squared plus 4 squared, and tangent of alpha equals 4 divided by 3. This gives r equals 5 and alpha equals 53.1 degrees, so 3 sine x plus 4 cosine x equals 5 sine of x plus 53.1 degrees. Checking at x equals 0, 5 sine of 53.1 degrees is approximately 4, which matches 3 sine 0 plus 4 cosine 0 equals 4. Now consider the area of a wedge-shaped region bounded by a polar curve, found using the formula area equals 1/2 integral of r squared d theta over the given angle range. Evaluating this integral over the relevant limits gives an area of 3 pi over 2. Checking, this value is positive and smaller than the area of the full circle of the same radius, as expected for a wedge. Next, we solve the differential equation, dy by dx plus y over x equals x, using an integrating factor. The integrating factor is e to the integral of 1 over x dx, which equals x. Multiplying through by x and integrating gives x times y equals x cubed over 3 plus c, so y equals x squared over 3 plus c over x. Checking, differentiating this y and substituting back into the original equation confirms both sides are equal. Now we solve the second order equation, y double prime minus 3y prime plus 2y equals 0, using the auxiliary equation m squared minus 3m plus 2 equals 0. Factorizing gives m equals 1 and m equals 2, so the general solution is y equals ae to the x plus be to the 2x. Checking, substituting this y and its derivatives back into the equation confirms it satisfies the equation for any constants a and b. Next, we evaluate two determinants. For a 2 by 2 matrix, the determinant is a times d minus b times c, and here this works out to negative 2. For a 3 by 3 matrix, expanding along the first row using the same rule for each 2 by 2 minor gives a determinant of 1. Checking, expanding along a different row gives the same value. Now we use vectors. The area of a triangle formed by two vectors equals 1/2 the magnitude of their vector product, and here this gives an area of 1/2 times the square root of 46. Using the same vectors, we also find the equation of a plane 6x minus 3y plus z minus 8 equals 0. Checking, substituting the known point into this equation gives 0, confirming the point lies on the plane. Next we sketch the curve, y equals x squared over x minus 2. This curve has a vertical asymptote at x equals 2, where the denominator becomes 0. Differentiating and setting the derivative to 0 gives turning points at x equals 0 and x equals 4. Checking, the sign of the derivative either side of these points confirms one is a maximum and the other a minimum. Now we solve the cubic equation, x cubed minus 6x squared plus 11 x minus 6 equals 0 by testing simple integer values. The roots are 1, 2, and 3, giving a sum of 6 and a product of 6. Checking, the sum of the roots matches negative the coefficient of x squared, and the product matches negative the constant term, since the leading coefficient is 1. Next, we prove by induction that 1 plus 2 plus up to n equals n times n plus 1, all divided by 2. We first check the base case n equals 1, where the left-hand side is 1, and the right-hand side is 1 times 2 over 2, which is also 1. We then assume the result is true for n equals k, and add k plus 1 to both sides, showing the sum up to k plus 1 equals k plus 1 times k plus 2, all divided by 2, matching the same formula with n replaced by k plus 1. Since the base case holds and the statement passes from k to k plus 1, the formula holds for all positive integers n by mathematical induction. Now we state the Maclaurin series for e to the x. It is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, continuing with x to the n over n factorial for all n. Checking substituting x equals 0 into this series gives 1, which matches e to the 0 equals 1. Next we define sin and cosh using exponentials. Sin of x equals e to the x minus e to the negative x, all divided by 2, and cosh of x equals e to the x plus e to the negative x, all divided by 2. Using these definitions, cosh squared, x minus sin squared, x equals 1, checking at x equals 0, cosh of 0 equals 1, and sin of 0 equals 0, so 1 squared minus 0 squared equals 1 as required. Now consider the ellipse x squared over 25 plus y squared over 9 equals 1. Here a squared equals 25 and b squared equals 9, so a equals 5 and b equals 3. The eccentricity is found using e equals the square root of 1 minus b squared over a squared, giving e equals 4/5. Checking, since b is less than a, the eccentricity lies between 0 and 1, as expected for an ellipse. Next we use integration by parts to find the integral of x times e to the x, using the rule integral of u dv equals uv minus integral of v du, with u equals x and dv equals e to the x dx. This gives integral of x e to the x dx equals x e to the x minus e to the x plus c. Checking, differentiating this result using the product rule returns x e to the x, confirming it is correct. Now we find an arc length using the formula arc length equals integral of the square root of 1 plus open bracket dy by dx close bracket squared dx. Evaluating this integral over the given limits gives an arc length of 14/3. Checking, this value is slightly larger than the straight line distance between the endpoints, as expected for a curved arc. Next, we estimate the integral of x squared from 0 to 2 using the trapezium rule, which states that the integral is approximately half the strip width times the sum of the first and last values plus twice the sum of the middle values. Applying this with the given strips gives an approximate value of 2.75. Checking, this is close to the exact value of the integral, which is 8/3, or approximately 2.67. Now we apply Euler's method for one step, using the rule y next equals y plus h times dy by dx, evaluated at the current point. Carrying out this one step gives y equals 1.1. Checking, this value is close to what we would expect from the exact solution over such a small step. Next we find the eigenvalues of a 2 by 2 matrix by solving the equation, the determinant of the matrix minus lambda times the identity matrix equals 0. This gives eigenvalues of 5 and 2 with corresponding eigenvectors 1, 1 and 1, -2. Checking multiplying the matrix by each eigenvector confirms it returns the eigenvector scaled by its eigenvalue. Now we applied de Moivre's theorem, which states that cosine theta plus e sin theta, all raised to the power n, equals cosine of n theta plus I sin of n theta. Applying this to the given expression gives a result of -1. Checking, this matches the expected value since the angle reached is an odd multiple of pi, where cosine is -1 and sine is 0. Next we find the fourth roots of unity, which are the solutions to z to the 4 equals 1. These roots are 1, I, -1 and -I. Checking, raising each of these to the power 4 gives 1 in every case. Now we find the radius of curvature of the curve y equals x squared at the point where x equals 1 using the formula radius of curvature equals the quantity 1 plus open bracket dy by dx close bracket squared, all raised to the power 3/2 divided by the second derivative of y. At x equals 1, dy by dx equals 2, and the second derivative equals 2, giving a radius of curvature of the quantity 1 plus 4 raised to the power 3 over 2 divided by 2. Checking, this simplifies to 5 times the square root of 5, all divided by 2, a sensible finite value since the curve is smoothly curving at that point. Finally, we confirm Lagrange's theorem using the fourth roots of unity as a group of order 4 under multiplication. Lagrange's theorem states that the order of any subgroup must divide the order of the group. Checking, the subgroup 1 and negative 1 has order 2, and 2 divides 4, confirming the theorem holds. This completes our tour through the whole of further mathematics in one continuous worked problem, from complex numbers and calculus through vectors and matrices to series, geometry, and group theory.